We're going to look at some chemical trends within the alkali metals, the halogens, and the noble gases. If we look at the alkali metals, those are the group 1A elements. As we go down the column, going from lithium down towards rubidium, we see that atomic radius, density, and reactivity all increase. Here's the table showing these things. So here's density. We see that the density increases. Atomic radius increases. All of these have very low ionization energies, so they're going to be very reactive. We do not find these elements uncombined in nature. You can't, you can find gold in little chunks. You can find veins of silver. You can't mine sodium in that way because sodium reacts with water in the air. There's just no way it's going to be sitting around. These guys are very good reducing agents because they're easy to oxidize because of their low ionization energies. And the compounds that they form are generally soluble in water. If you remember those solubility rules we learned, lithium, sodium, potassium compounds are always soluble. So the reactions of alkali metals. There are two that you should be familiar with. Alkali metals will react vigorously with nonmetals, such as the halogens. So if you have an alkali metal with a halogen, so perhaps sodium and chlorine, they will react vigorously and form sodium chloride. We can predict the formula of these by looking at the ionic charges that the elements involved take. And the alkali metals react explosively with water. So if you take one of the alkali metals, and here are pictures of them doing this, small quantities of the metal in a beaker of water. The metal reacts with water to form an ion, and hydroxide ion, and hydrogen gas. So essentially they are forming the metal hydroxide, which is soluble, and so it's written here, separated out, and then it forms hydrogen gas. And this does so very exothermically, and so it generates enough heat to ignite the hydrogen gas, which is very flammable. So you can get some really fun explosions going on. Which is why things like sodium are kept under lock and key to keep students from tossing them into a sink full of water and blowing up half the lab, because it's just not a good idea. Which half? The half that the sink was in, including their heads.
Like what ratio of sodium to water? Like how big did it have?
Well, it would really depend. I think if you had finely divided sodium, a lot of small pieces of it, it would react a lot more violently than if you had one giant chunk. But you can go on YouTube and find pictures, videos of people throwing things like sodium or lithium into swimming pools. It's pretty entertaining.
So if you just have like a tablespoon of it, and just put it in.
Yeah, it'll generate hydrogen gas and set the hydrogen gas on fire.
Sounds like a joke. Hey, would you like some sodium with your coffee? Boom.
Boom, yeah.
So, you said it reacted with the water in the air.
Mm-hmm.
How violently would it react with that?
Well, I don't think it would react real violently with the moisture in the air because there's just not a lot of it. But you can't just have a piece of sodium and keep it in a bottle like we do other chemicals, because there's going to be enough moisture in there that's going to completely react the outer layer at least. And so metals like this are either stored under a noble gas, or more frequently they're stored in some sort of an oil. So I don't even know if we have any sodium. There's not really a good reason for keeping sodium metal around, but it has to be stored in like mineral oil or something to prevent it from just reacting all by itself.
So you said if it was under a noble gas, like what gas?
Well, like neon or argon or something.
You just like pump the container with that gas?
Mm-hmm. Yeah, and so, and we'll get to that when we talk about the the noble gases. We're going to talk about them too. So the halogens also have some nice chemical trends. As we go down the column, atomic radius and density increase. The melting point actually decreases for the halogens. That's the opposite of the alkali metals. We see that ionization energy decreases and reactivity decreases. So for the alkali metals, it increases. These have very high electron affinities. That makes them very good oxidizing agents because they're very easy to reduce. These are also very reactive, and we don't find them uncombined in nature, and their compounds are generally soluble. And there's a table showing the different features of them. So, two types of reactions of halogens we should be familiar with. This is the same one we saw with the alkali metals, but in general, halogens will react with other metals as well. And so it just depends on the charge that that metal ion takes, what the formula of this compound is. But they'll form metal halides. And they will react with hydrogen to form hydrogen halides. So this is going to look like an acid, HCl, HF, HI, etc. But when these react in the gas state, they're going to form the pure compound in the gas state, and that's not an acid. It's an acid when it's dissolved in water.
So don't breathe it in.
No, you should not breathe it in. Because if you breathe in, say, hydrogen chloride, what's on the inside of your nose? Moisture. And so it will dissolve in the moisture on the inside of your nose and form hydrochloric acid, which is quite painful. And you breathe it in further, it gets in your lungs, really bad stuff to inhale. Okay, so let's write some balanced chemical equations for each reaction. These are the sorts of problems I always hated as a student, because they just seem so general. The reaction between aluminum metal and chlorine gas. So we just said that metals and halogens react to form metal halides. So that's what's going to happen here. We've got aluminum, and aluminum is a solid at room temperature, reacting with chlorine. We need to remember that chlorine is a diatomic element and write it as Cl2. And they told us it's in the gas state. So what are these going to form? Aluminum forms a positive ion. Chlorine forms a negative ion. What's the charge on an aluminum ion? +3. And what's the charge on a chloride ion? -1. So the formula for the compound that forms between them is going to be AlCl3. What do you think the state of that's going to be? Ionic compounds tend to have very high melting points. Salt melts at like thousands of degrees. Solid. It's going to be solid at room temperature.
Is that where the solubility?
Well, we would have to consider solubility rules if we had water involved. But here we have a solid chunk of aluminum and we have chlorine gas. It doesn't say anything about water being present. So then we should not say aqueous. Then we need to balance this. We've got a 2 here and a 3 here. We've got an odd-even issue, so let's double this to make it even. So now we've got 6 chlorines over here, so we can put a 3 in front of the chlorine on the left and get 6, and then we'll put a 2 in front of aluminum, and it'll be balanced. Any questions about that one? How about the reaction between lithium metal and liquid water? So lithium is a metal. What is its state, do you think? Solid. And liquid water. Now this one takes a little bit of remembering. This is that explosive reaction, right? What's the gas that's made that explodes? Hydrogen gas. So we're going to get hydrogen gas. And then we're going to get some ions. So we're going to have lithium ion and hydroxide ion. So lithium is +1, hydroxide is -1. In the slide where we showed this, it showed them separated, lithium ion and hydroxide ion separately. You can write them together. Lithium hydroxide. What should we write for the state of that? Aqueous. Lithium hydroxide by itself would be a solid, but this is happening in liquid water. And lithium hydroxide is soluble because all lithium compounds are soluble. So this is aqueous. Is this balanced?
No.
Not quite. We've got one extra hydrogen over here. So if I make 2 lithium hydroxides, then I could put a 2 in front of the H2O. I've got 4 hydrogens on each side now. I've got 2 oxygens on each side, and so I need to fix the lithium by putting a 2 here. The thing about doing a question like this, say on an exam, the key is to not lose your head. Don't panic, right? Say, well, let's think about it. Let's see if I can pull together some things that I know or make some reasonable guesses and at least take a shot at it. What about the reaction between gaseous hydrogen and liquid bromine? Well, hydrogen is a diatomic element. You need to do H2. That's a gas. And liquid bromine, bromine's also diatomic. What are those going to do together? Hydrogen bromide.
Oh.
Isn't that what you said?
Yeah.
Yeah, that's what I said. HBr. So hydrogen and halogens react to form hydrogen halides. And all of the halides form -1 ions, and hydrogen forms a +1 ion. And so it's going to be HX, HBr, HI, HF. And these are going to be gases. Is that balanced? No. Just put a 2 over here and then we'll be good. Any questions? Let's look at the noble gases. Again, we see that atomic radius and density increase as we're going down. Boiling point also increases. And the ionization energy decreases. But the ionization energy is so high that it just doesn't even really matter. The noble gases are exceptionally unreactive. It wasn't until the 1960s that someone was able to make a compound involving any of the noble gases. And as far as I know, we still don't know of any compounds involving helium or neon. Just nobody's done it. And that's one of those things that some scientists take as a personal challenge, right? They're like, oh, so there's no compounds? I'm going to try to make one. I'm going to devote my life to making a noble gas compound, even if there's no practical benefit in it. Science does not have to be practical. So we can use the noble gases as inert atmospheres when reactions with other gases would be undesirable. So if you want lithium or sodium metal and you want to store it without putting it in oil or something, you can store it under a noble gas. The noble gas will not react with it. End of chapter 8.